Hello everyone, my name is Alaeddine, and in this video we will cover the topic of floating point arithmetic, specifically the operation of multiplication. We can solve floating point multiplication similarly to how we solve regular multiplication. We have to follow these steps. First, we start off by normalizing each of the given expressions, adding their exponents and multiplying their significance. Then, we have to renormalize the answer if necessary. Following that, we round and we renormalize again, and then we end with determining the sign of the product. Let's start off by taking an example of decimal multiplication. Let's assume that x is equal to minus 53 and that y is equal to 195. Normalizing x and y would result in x equal to minus 5.3 times 10 and y equals to 1.95 times 10 to the power 2. Adding their exponents together would result in e is equal to 1 plus 2, which equals to 3. Now, we must multiply their significance. Let's take that the significand of x of s, is equal to 5.3, and the significand of y of s, is equal to 1.95. Multiplying these two digits together would result in x of s times y of s is equal to 10.335. In this case, our result is no longer normalized, so we must renormalize it. So we obtain that x of s times y of s is equal to 1.0335 times 10. So now we can deduce that x times y is equal to x of s times y of s times 10 to the power of the exponent is equal to 1.0335 times 10 to the power 4. Now, we must round, then renormalize our answer from earlier. Rounding will give us x times y is equal to 1.034 times 10 to the power 4. In this case, renormalizing is not necessary since the answer that we obtained after rounding is still normalized. The last step to do is to determine the sign. We do that by checking the signs of the multiplicand and the multiplier. If the signs are the same, then our resulting sign would be positive, but in this case, both our multiplicand and the multiplier had opposite signs, so our resulting sign is negative, thus leading to a final answer of x times y is equal to minus 1.034 times 10 to the power 4. Now, let's take an example of floating point multiplication. Let's assume that we are given these two decimal digits. X is equal to minus 13.4375 and y is equal to 270.625. First, we started by finding the binary representation of both these digits, as shown here. Then, we normalize both of these binary representations to obtain the expressions shown below. In some cases, we may be asked to represent x and y in 32-bit or 64-bit precision, which I will be doing in the next slide. Here, we have the 32-bit precision representation of x and y. My first bit represents the sign bit, and it is equal to 1 in case the decimal digit is negative, and it's equal to 0 in case the decimal digit is positive. Then, it is followed by an 8-bit exponent representation, which can be found by biasing the power of 2 in the normalized expression found earlier. As for the remaining 23 bits, they are known as the mantessa, and they are the binary digits found after the dot from our normalized expression. Now, we can add the exponents of the normalized expression found earlier. We obtain that e is equal to 3 plus 8 is equal to 11 for unbiased exponents, or 138 in case the exponent is biased. Now, we must multiply the significance. We take x of s to be equal to 1 point followed by the mantessa, and y of s to be equal to 1 point followed by its mantessa. As we've seen earlier in the decimal multiplication, we have x naught y is equal to x of s times y of s times 2 of e. In this case, we use a 2 to the power e instead of a 10 to the power e since we are multiplying binary numbers. Now that we have the values of x of s and y of s, we can neglect the rightmost zeros up till the first one since they won't affect our answer. So now we would have x of s is equal to 1.1010111 and y of s is equal to 1.00001110101. As we know in multiplication, x of s times y of s is equal to y of s times x of s. That is because the multiplicand and the multiplier are interchangeable. In this case, we will be working with y of s times x of s, since we want y of s to be the multiplicand and x of s to be the multiplier. The reason being that y of s has more bits after the decimal as compared to x of s. Doing so would make our multiplication process easier. In this slide, we will be multiplying the significance. We start with the rightmost bit of the multiplier. Since it is a 1, then we can just copy the multiplicand as it is. That is because 1 times x will always give us the value of x. Then, when we move to the second bit from the right, we must first start by placing a 0 as shown in red. We will be doing this every time we move to another bit. This is also typically done with regular decimal multiplication. Once we reach a bit that is 0, then we will simply just have a row full of zeros. That is because 0 multiplied by anything will give us a 0. Once we are done multiplying, and we reach the leftmost bit of the multiplier, then we have to add all of these expressions together. We need to make sure that our result will have the decimal dot in the same location as the last multiplied expression, which is obtained when multiplying the leftmost bit of the multiplier with the multiplicand. Once we are done, we must round and renormalize. In this case, rounding is not necessary since the 23rd bit after the decimal dot is 0. However, it would be necessary if the 23rd bit was equal to 1. In this case, since we did not round, then renormalization is not necessary, and the product that we obtain is shown here. The last step to do is to determine the sign. In this case, since our multiplicand and the multiplier have opposite signs, that means that our product will have a negative sign. This is represented with a sign bit of 1. Now we can represent our product in 32-bit precision as follows. Our sign bit will be equal to 1 since our product is negative. We will have our 8-bit exponent expression equal to 138 in decimal for the biased value, or equal to 11 for the unbiased values, followed by 23 bits of the mantissa, which we can find by checking the bits after the decimal dot in our product, followed by a certain number of zeros to fill up the remaining 23 spots. Once we are done, we may want to make sure of our answer. To do so, we must convert the 32-bit precision expression into decimal. We have to use this formula. X times y is equal to minus 1 to the power sign into 1 plus the fraction into 2 to the power e minus 127. In this case, the sign is equal to 1 since our product is negative. Our fraction can be calculated from the mantissa section of the 32-bit precision expression, and our exponent is equal to 138 biased. From this, we obtain a product equal to minus 3,636.523437. If you were to plug our initial decimal values onto the calculator, we would obtain a product of minus 3,636.523438. As we can see, the answers are almost similar with a very small rounding error. Here are some real-life examples. Floating point multiplication is a crucial operation in high-power computing applications such as image processing and signal processing. Some additional information about floating point multiplication is that the multiplier has a similar complexity to that of the adder. The only difference is that it uses a multiplier for significance instead of an adder. Also, the operation can take several cycles, but it can be pipelined.